Hey guys! Woohoo! I am super excited. I have a new computer and I know you can't see it, but I can. It's right here. so, so we haven't done like a traditional show in a little while because a lot has been going on. A lot of stuff has been like shuffled around. I've been getting the new computer in and we've been having coffee chats, talking about different things. So string theory. Oh my gosh. I have been up since about 6 this morning putting stuff together. I had started trying to dig down a little bit for it to figure out stuff. But oh my goodness. String theory. It can be mind blowing to a lot of different individuals, but that's okay. We're going to sort it out and it's going to be pretty groovy today. So, we've got new patrons in, and so we update like the patron video at the beginning. And Bull, you have some new stuff you can show on your shows that you produce. What do you think about that?
That's great, and I have to thank Peter for that. That was really awesome of him to do those for me. That's gonna go for it in the chat, and we love you, guy.
Awesome. Yeah, I thought that was pretty cool. So, Bull is Bull's my producer, so I have a producer, which is awesome. So, we pay him. I pay him and the Geek Room pays him. And if you're interested in him producing your shows, be certain to get in contact. If you can't find him somewhere, I'm pretty accessible. Shoot me a message and I'll get y'all connected if you need a producer for your show. He does good work. So we got so many people in the chat. Good morning, everyone. Good morning. We got Dennis Hands on Periscope. We got Wayne, Peter, gonna go for it. Nana, what's up? Nether's here. So we're gonna talk about all things string theory. So you guys want to get started? It's a hefty topic, but I'm hoping I can break it down to simplistic terms for you. So, all right, string theory. It's not just the preferred theory from cats, So let's pop it up. What are we going to talk about? Here we go. So initially, this was going to be back in July, but, I am not a particle physicist. I'm not a quantum physicist, and I recognize that. So hopscotch, it's 5 in the afternoon. Yes, it is. Sorry about that. It's morning where I'm at, so that's why on Twitter I said good morning, afternoon, and evening, because you never know where people are going to be in relation to the world. So string theory is pretty heavy. So usually I have a pretty broad knowledge. String theory is pretty challenging for a lot of individuals, but a lot of it has to do with mathematics, and people freak out. They're like, oh my gosh, the math. Hello, Hair Lady 25. Okay, so what are we going to talk about? What are the different questions we're going to answer? So essentially what we're going to kind of discuss is, what is string theory? What is it? Is there evidence for it? Is there evidence for string theory? Well, short answer is no. No, there's not, but that's okay. We're going to talk about different things, what leading to that, and what we have to overcome, the research that's needed in order to get the evidence for string theory. We're also going to talk about the challenges and the issues associated with that. Now, when we've talked about expanding universe, that kind of solves a lot of the issues associated with the Big Bang Theory. So, science does change when we get new information, and a lot of the models that we have were originally based on mathematics. So what's the breakdown of theory? Well, essentially we have M theory. String theory started out in the early 1950s. It was mostly about bosons, which is a type of elementary particle. Now, I have done an entire episode just on elementary particles, and you can check out that on my channel, the science of, I believe it's quantum particles or subatomic particles. You can check that out, and I talk about what each individual elementary particle is and what they do. So this is an attempt at just trying to figure out what the theory of everything is. How is everything interconnected? In this particular theory, with M theory or superstring theory, particles are not dots, but they're one-dimensional vibrating loops or strings, essentially. Rather than being a singular point within, the universe, it's a string, and it can be long, it can be finite, it can be a loop, and they all vibrate. So the type of vibrations are exclusive to the particle type. So, excuse me, bosons vibrate a certain way. We would expect gravitons to vibrate in a certain way. Electrons vibrate in a certain way, and those vibrations are associated with the properties that we can measure: mass, charge, that sort of thing. String theory also provides a mathematics of holding atomic nuclei together, and it requires about 11 different dimensions for the overall M theory. All right, so let's dive into this a bit more. I'm going to check up on the chat a little bit. Hello, everyone. I'm not a scientist, but I have stayed at Holiday Inn. So have I. But I have been a scientist, though. I have done research. So, but I have stayed at a Holiday Inn. So I don't know if that is a qualifier for anything else. That's a good question. I've stayed at a Holiday Inn, therefore I don't know. I'm not very creative this morning. What is the string made of? Says Dennis R. Hand. See, that's a good question. We have to be able to detect them. We don't know yet. So let's talk a bit about what string theory is. It's a mathematical way of describing how forces hold each other together. The atomic nucleus. So when you're talking about atomic theory and you're looking at the nucleus of an atom, for all intents and purposes, is a bit of a wonder in itself, but we do know that protons and neutrons are the main particles of the atomic nucleus. Protons are positively charged, and in practice, without something to regulate them, the nucleus would be ripped apart because like charges repel. So when you increase the amount of protons in an atom, you have to increase the amount of neutrons in order for it to be stable. Now we understand that there is a force there, the strong force that kind of connects and holds the neutrons to the protons. The kind of way that I think about it is, if you're in a club, your neutrons are your bouncers. Your protons are those supercharged energy particles, like, this is my song, and then they go and flood the dance floor. Well, if you don't have neutrons in place there, the whole club is probably going to come down, or, you're going to have an explosive type of dancing, and which is fun and all, but, you got to kind of think about it. The string is a model. Well, it's a model of how things are connected to each other. We're going to get into a little bit why the idea of a string is a lot more, is kind of sorts some of the issues than it just being a particle. All right. All right. So the strong force that binds neutrons to the protons is one of the 4 fundamental forces that we see and can measure in the universe. We have strong forces, electromagnetic forces, weak forces, and gravity. Now, what exactly makes up gravity? We do have the graviton particle, but we do not have a strong understanding of gravity like we do with electromagnetic, weak, and strong forces. Now, we also have yet to find the graviton. Now, we understand and can accurately predict all of the other forces at all scales and distances. This is not the case with gravity at very short distances. So when we're looking at less than a Planck length, so we're talking teeny, 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 tiny lengths, gravity, the whole idea of it, it just falls apart. String theory fills in those gaps with nothing less than mathematics. Now, to be fair, math has done us a lot of good in predicting the existence of atoms just through showing that they move. There's something called Brownian motion. To this day, we still use, Einstein mathematically proved the existence of atoms, showing that they move. If you have a glass of water and you have pollen particles in there, Brown, I believe, was a botanist. And so he noticed that pollen moves in a glass of water. If there's nothing shaking it around, you can see these movements. And so Einstein proved the existence of atoms by showing that they move. And that's what we call Brownian motion. To this day, we still use Einstein's equations to help us determine the size of particles on the nanoscale based on how they scatter light. That particular instrument is called the dynamic light scattering instrument. All right, let me check up on the chat. No wonder we feel at home in other chat. We got some chat going on. People feel at home. The string isn't really made from anything. It's a mathematic description of subatomic behavior of nature. Yes, we know things act a certain way. We have particles that spin certain ways. We have things associated with gravity, weak forces, strong forces, electromagnetic being photons. We have all of these different behaviors. So yes, the thing, and we'll get into this in a minute. I don't want to jump too ahead because I don't want to lose people, because it's kind of like, that's the educator in me. We have to kind of follow this train of thought. And since we have a diverse group of individuals watching us with different levels and varying levels of understanding, let's see. Our YouTube comments not showing up on the restream. We might want to pop over, Bull, to the YouTube comments for the side chat on the screen. Just if you can switch between the two. It's weird. I'll be honest. The restream chat that I have, for whatever reason, it doesn't pop up for, I don't know what it is. Since Restream changed the way that they do the chat, my YouTube comments don't show up on the Restream chat, so I have to hold up a separate box on here. So that's a bug that Restream hasn't worked out yet. So that really kind of sucks. All right. So let's pull up this little thing of what we know when it comes to gravity, because gravity is essentially what it is that we're looking at for the 11-dimensional aspect of string theory. So what we know, let's pop over and have a look at what it is that we know and what we don't have. All right, so what we know, we understand classical gravity. All right, we do understand classical gravity. So like large scale gravity, we can predict how things go. We can even correct for quantum mechanical gravity through mathematical corrections. But what we don't have is a complete theory of gravity. So these are the kind of things that string theory kind of fills in with that. So it's a bit of a problem with that. All right, so let's discuss a bit further what the issues with gravity are and how does string theory involve math to fix it. All right, we are able to calculate correction to quantum gravity as long as we are at energies below the Planck mass. Okay, so that's about the mass of a flea egg, teeny tiny little bit mass. But when we study processes at the order of Planck mass, more and more parameters are needed in order to make those quantum gravitational mathematical corrections. So because gravity, we don't quite understand how well it works on that teeny tiny little level because we've yet to find the graviton. We can't really do lots of experiments with it. We have to make mathematical corrections, but the smaller scale we go, the more parameters are needed to make those corrections. So now remember, we're talking about ridiculously small, tiny sizes of things. And gravity fundamentally is elusive to us on this small scale. So how does string theory fix all of this? That's what we're going to talk about. Let me catch up on the chat. We're still talking about Holland and stuff. Hey, guys. There is no string, only wood. Well, I have string going on with my hair right now. I got lots of strings, and it's made out of protein. But I know they're curled because of things called hydrogen bonds between the varying groups. It's fun. All right. I'm going to tell you guys, it's been pretty mind-blowing this morning because, you know, string theory, it's pretty cool. Lots of things have been proven, you know, lots of things had shown to mathematically work in the past. And we didn't have the instruments or the experiments yet to prove that they exist until much later, you know. Even with the helical structure of DNA, they looked at, you know, Rosalind Franklin's crystallography, X-ray crystallography, was able to show that it had a bit of a helical pattern. So the time they had X-ray crystallography, but they had to work out how it actually fit together. And then they sorted out all the hydrogen bonding, the different ladders, you know, like the twisted ladder. But we now have scanning tunneling electron microscopy, which allows us to actually see this helical structure of DNA. So while we yet to really have the instrumentation to kind of help us be able to detect things, you know, it's still, the math still kind of held up prior to that. All right, so let's talk about, let's go to the next thing. String theory, quantum gravity fix. This is what it is. Hello, everyone in the chat. So let's take a look at what the electron is. All right, so let's kind of break this down. Let's go with the fact that the electron is now a string. So instead of just being this little particle, it has this, it's extended. So it has what we would call a finite extent, a limitless extent. Well, in that regard, there are no additional parameters needed in order to correct for this particular gravity issue. So they don't need to add any more. That only leaves just one unknown parameter versus loads of unknown parameters for the calculations. And that means the length of the string. So instead of thinking of an electron as a dot that goes around the nucleus, it's now a string. And all of these different particles, including like bosons and these sorts of things, they all have strings instead of being just a dot. Same thing with gravitons. So if we're able to kind of lengthen the particle with this idea of these strings all interconnected into where they can interact with each other, that allows us the ability to make calculations without having to worry about all of these extra parameters. Smaller scale that we go. Let's have a look at this particular graphic. This is essentially when we're looking at in practice the structure of an atom. All right, so each one of these are little loops. Essentially, with Michio Kaku, Dr. Michio Kaku, one of the theoretical physicists who worked with string theory, the universe is a symphony of vibrating strings. So essentially, string theory proposes that all matter and energy are made up of incredibly tiny one-dimensional vibrating strings of energy about 10 to the negative 35 meters long. NASA, okay, I love the NASA site. The thing I like about the NASA site is that it has so many varying levels of challenging material, anywhere from they have content that you can give to little preschoolers all the way to more challenging information up onto like the doctorate level. And they have kind of a really nice breakdown of string theory. And this is what they have to say. So in the current understanding of the theory, those strings are not made of anything. There you go, Nether. Kind of reinforce that. They are a fundamental constituent of matter. The consequences of replacing point-like particles by vibrating microscopic strings are enormous. The only consistent framework to describe those strings implies a 10 or even conceivably an 11-dimension world in which 6 or 7 dimensions are all curled up, okay? Those extra dimensions are the ones which determine the properties of the world we live in. The larger dimensions, the one that we see, are what we perceive as the ordinary space and time. So, with that in mind, there are different types of string theory, and they all come together to form what we call M theory. So take a look at this picture. So here's all the different ones. So M theory is superstring theory. Now, if we want to get into the history of string theory, it started out initially involving bosons. All right. If you'd like to learn more about bosons, I mentioned it before, I did a whole episode just on elementary particles, the science of subatomic particles, elementary particles per se. Check it out. You can find it in my playlist, The Science Of. You can look there. And if I have a shortened version of it, it would be in my ScientistMel Shorts playlist. Now let's discuss the different types of string theory in relation to bosons and the ever-elusive gravitons and how they come together to form superstring theory with supersymmetry, also known as M theory. So here we have this graphic. And this is M theory. So we have type 1 string theory. It involves both open and closed strings. It contains a form of symmetry that's mathematically designated as a symmetry group called O32. That sounds almost like some kind of space movie, I think. You know, symmetry group O32, you know. Maybe we should write one. Maybe we should write like a space sci-fi film called O32. That'd be kind of cool. And then it would be scientifically inaccurate, and I would be mad because that's the way it would go. They would just change it. Okay. Anywho, type 2A string theory involves closed strings where the vibrational patterns are symmetrical, regardless of whether they travel left or right. Okay, so they're always symmetrical, whether they're moving left or right, either way. Type 2 open strings are attached to structures that they call D-branes, and those types have an odd number of dimensions. We could spend a long time just discussing string theory, and then at the end of that, we would all be exhausted because this is quite brain heavy for that sort of thing. All right, so let's talk about type 2B, okay, string theory. It involves closed strings where the vibrational patterns are asymmetrical, but that depends on whether they travel left or right along the closed string. All right. Now, type 2B open strings are attached to the D-branes that we talked about in type 2A, and it's D-VRANES. And those were discovered in 1995, and those have an even number of dimensions. Now, keep in mind, we understand like the boson particles and that sort of thing a lot better, particularly because of the Hadron Collider, where we were able to find the existence of the Higgs boson. So lots of work going on with CERN trying to get this done. Now, a new form of string theory, kind of new, is called heterotic. It almost looks like heterotic. Yeah, heterotic string theory was discovered in 1985 by the Princeton team of David Gross, Jeff Harvey, Emil Martinek, and Ryan Rome. Now, this version of string theory sometimes acted like the bosonic string theory, but sometimes acted like the superstring theory. Now, the difference between the heterotic string is that the string vibrations are different directions, resulting in different behavior. So we have left moving vibrations resemble the old bosonic string, while the right moving vibrations resemble the type 2 strings. But the heterotic strings seem to contain exactly the properties that Green and Schwartz needed to cancel out the anomalies within the theory. All right, I know I'm saving lots of words here, and it's just kind of woo. I'll catch up on the chat here in just a second. I haven't forgotten you guys. I don't want you to think that. This is kind of heavy stuff, and I'm trying to get through the different types for you. All right, but the thing is here, it was ultimately shown that only 2 mathematical symmetry groups could be applied to that particular heterotic string theory. This resulted in stable theories in 10 dimensions, O32 symmetry and E8 by E8 symmetry. Now, those 2 groups gave rise to the types that we see, type HO and type HE string theory. Now, stay with me. Type HO. That sounds almost like a punk band, almost like Type O Negative. That wasn't a punk band, though, was it? That was Bull. Do you know about Type O Negative, that band?
Yeah, I've heard of them.
You've heard of them? I don't remember what genre they would fall into.
I think they were punk.
They were punk? Okay. So we need type HO. Now, this particular string theory, it's heterotic string theory. This name comes from the longer name, the heterotic O32, Remember we mentioned that before, string theory. And it describes the symmetry group of the theory. It contains only closed strings whose right moving vibrations resemble type 2 and whose left moving vibrations resemble the bosonic strings. The similar theory HE has subtle but important mathematical differences regarding the symmetry group. Type HE string theory. I'm almost done. Not one string theory is perfect. This is what I'm trying to go. These all talk about the different vibrations of different particles regarding the bosonic. And then we talk about gravitons and the 11-dimensional supergravity type of string theory. But the thing is when they all come together due to the way the dim theory. So if this is like way too much, just keep this in mind. There are these different types of string theories come together from the main one. So the last one, HE string theory. It's another form of heterotic string theory, but it's based on a different symmetry group from the HO theory. It comes from the longer name, the heterotic E8 by E8, which we kind of see there. And it's based on the symmetry group of the theory. It also contains only closed strings whose moving vibrations, the type 2 strings, left moving vibrations resemble the bosonic strings, like that. All right, so we have type 1, 2A, 2B, E8 by E8, SO32, and 11-dimensional supergravity. I haven't even had breakfast yet, and I'm tired already with the braining, but that's okay. This is really cool stuff. All right, let's catch up on the chat, and let me get, we're going to talk about the 11-dimensional gravity, man. 11-dimensional gravity. Can you guys imagine all of the other dimensions? It's pretty cool. All right, Wayne Terry. I was at home relaxing doing some decorating, but now my head is spinning with string theory. Woohoo! Oh, wow, I need educating. You're welcome. Let's see. I think Nather had a joke somewhere. I'm trying to find it. I thought she had a joke. I'm trying to find the joke. Let me scroll back, see if I can find it. What was your joke, Nether? It vanished. Yes, it's hard to make it precise predictions that we can test. You're right about that, Nether, when it comes to this. Unequal expansion is one of the many possibilities covered by string. One problem with string is that it predicts two broad ranges of possible universes. Yes, we're going to talk about the challenges. Nether is up on this stuff. There's the joke. Why does string predict 11 dimensions? The math doesn't work out with less. Yeah, that's true, actually. We need 11 dimensions for string theory to work. Oh my goodness. It's like asking how Newton's laws of motions explain traffic jams. You can connect those things in the end, but that's a long walk for a short drink of water. That's true. That's true. You're in the live chat because my headphones died when I got to the gym. That sucks, Tad Philosophy. Get in there, get strong, man. All right. So I think I've been caught up. All models are wrong, but some are useful. George Ball. Well, we got the quantum model. The atomic quantum model is pretty accurate. It's the best working one we've got. But, to be fair, if you just go through atomic theory and you look at the different models and how they've changed over time, started out as like little billiard balls. And we thought that, cheese was made out of cheese atoms and, people were made out of people atoms. And, at least they got the idea that big things are made out of smaller things put together. And kind of coincides a bit with cell theory on that. But the models get better over time. And that's just kind of what it is the more we understand things, the more we can shift and change the models. So that's pretty groovy. So let's talk about these 11 dimensions. It is thought that these dimensions, given we are discussing things on a quantum level, teeny tiny spooky weirdness happens on the quantum level. These are so small that we may not be able to detect them. They are described as being super curled up in extremely tiny space at 10 to the negative 33 centimeters. So essentially, that's 10 with 31 zeros in front of it as a decimal. So yeah, we can't see that. But we're trying. We're trying. So string theory has been applied to all kinds of research, though, to try and understand what happens inside of a black hole, to attempt to simulate the Big Bang and understand dark energy a bit better. But while we don't have evidence of string theory, we really don't, it certainly is moving towards being useful in understanding other portions of the universe, at least pointing us in the right direction of where we kind of need to focus on, developing instrumentation. So, Nether, it's all about you now, man. Let's talk about the different issues. There are issues associated with string theory because you know what? Nothing's perfect and it's all kinds of nuttiness going on. Here's the problem with string theory. Kind of taps into this multiverse idea. There would be a huge number of universes, 10 to the 500. So essentially that's 10 with 500 zeros after it. I don't even know what that number is, to be honest. What's 10 with 500 zeros after it? Anybody want to Google that? Let me know if you can find out what that's called. I know a Google is a one with, is that a million? A million zeros after it? Is that a Google? Or is a thousand? I can't remember. A Google used to be.
Google was, and it's spelled different too. Google
Yeah.
is it's 10 to the 100th power.
Okay, so this is 5 times a Google.
Right, and then but there was also one called a Googleplex, which is a Google to the Google power. Which is just a massively insane, like, meaningless number at that point.
Oh my goodness. So yes. Okay, a Google is 10 to the 15. Okay, the 10 to the 15. So, everything is crazy. So essentially, if you can imagine a 10 with 500 zeros after it, here's the issue with string theory. You have this huge number of universes, and they would lack any that look like ours. There's no dark energy described. There have been papers that have been published. Now, if you're curious about my sources, I will show you a whole bunch of links. There is a math paper, or there's an intro to string theory. There's a particular document that they have from Berkeley. It's available in PDF form. I was going through that quite a bit. That's a heck of a read. So if you want something more challenging, so Nether, this would be cool for you. You're here to learn more. Fantastic. If you want something more challenging, there is a document that they use for intro to string theory through Berkeley, and it's all about the math. And a lot of the string theory equations have been shown that have been called elegant. So if you're wanting to kind of play around with the different equations and see what the math looks like on that, you can check that out. But there have been publications that have come out that have been criticizing string theory because a lot of these different universes, there's no dark energy that would be described in them. There's also endless mathematical constructions. So all of these different mathematical constructions, we would have no known relationship to what we observe. So if we can't observe it, that makes it a particularly problematic issue. And we don't have the tech yet. That doesn't mean that it's not possible. They are trying, but we just don't have the tech yet. All right, so is it testable? We have, let's see, what do we need? What is the evidence that we need in order to test string theory? Measuring smaller dimensions. So we're talking about ridiculously small 31 zeros in front of 10 decimal place. 31 decimal place is ahead of that small, okay? So we have limits on our detection. We cannot measure anything that small right now. We need to be able to find something called supersymmetry. All right, what is supersymmetry? Well, we can kind of see this. We're hoping to be able to find it through the Hadron Collider. Supersymmetry would link the two different classes of particles that we know as fermions and bosons. Again, if you're not familiar with these subatomic particles, I did do a show just on that. So don't feel discouraged. You can check that out. Now, these particles are like those in the standard model that we have for quantum theory. And they're classified as fermions or bosons based on their spin, which direction they spin, forwards, backwards, left, right. Fermions all have half of a unit of spin, while bosons have 0, 1, or 2 units of spin. Now, supersymmetry predicts that each of these particles in our quantum standard model, they have a partner with a spin that differs by half a unit. Now, the thing that's really cool is the discovery of the Higgs boson helps reinforce our idea of supersymmetry, but it is the hope with the Hadron Collider that we're able to find these supersymmetry particles. So if string theory is true, we should be able to find supersymmetry at some point in time within the Hadron Collider by finding those particular particles. We also need to be able to have evidence of the holographic principle, essentially that which we call the multiverse, which is something that's still kind of hard to nail down. We can kind of see the phasing in and out of particles, you know, the fact that neutrinos are around. We can finally detect those with that huge neutrino detector in Japan. But still, there's lots of challenges that associate with that. And if we're able to develop instrumentation on being able to detect those smaller dimensions, if we're able to find that supersymmetry in particles through the Hadron Collider, that doesn't necessarily prove string theory, but it'll bring us closer to saying, okay, one step forward towards that being a possibility. There are some philosophers that say because string theory is the only working model, or superstring theory, the M theory, is the only working model, mathematically kind of fits, that it must be true. Well, you got to kind of be careful of that hole, because we all know that just because this particular thing seems to work right now doesn't mean that it's 100% true. Models change, and that's okay. And that's kind of what we have to keep in mind with that. All right, let's get back to the chat. Let's get back to the universes. Can you imagine? That would be a cool movie, wouldn't it? 10 to the 500. Think of all the different universes. See, I hated the film Inception because it was a dream within a dream within a dream within a dream. But can you imagine a film that was called 10 to the 500? Hey, Geek Room, what's up? Because that would be a cool movie. What if you could pass between 10 to the 500 universes? Wasn't there like the one Quantum Leap? What was that? Sliders? Was that the name of that show where they went through different universes?
Yeah, they kept sliding and they couldn't get back to their own.
Yeah, so my 10 to the 500 movie is already shot because they had a whole TV series of that. See, I can't win, Bull. Can't win. Not at all. All right. So when it comes right to it, what are we talking about? String theory, superstring theory, or M theory, is the closest thing we have right now to the theory of everything, how everything is interconnected to others. But limitations on our instrumentation to detect small dimensions, prove multiverses, finding the graviton, all propose challenges that science must come in order to even have it on an observable scale. If we're able to find the graviton, that would help resolve a lot of the issues, because then we could study how it behaves on the quantum level. But we haven't even found it yet. Mathematics are still a strong tool in proving the existence of things before we can test them. We have seen this with the Higgs boson, atomic theory, and relativity before experiments prove them to be true. That's the thing with science. The imagination of how it is that a thing works, showing its existence in known observable equations, then looking for ways to test it, has been what drives us to find ways to test their existence. Math leads to the truth. Even if you don't like math, it's kind of exciting in itself, don't you think? You know, Let's see, one thing string theory will always have, at least it's mathematically true. One of the few scientific theories that has actual proof, since that's reserved for math and logic. Yes. So it ties everything up in a nice bow. Kind of like how the expanding universe, or, kind of ties up the Big Bang in a nice bow. All of these different things. I mean, it's like amendments. You have, okay, this is what the math says. Oh, wait, we have a problem here. How can we sort this problem? Hey, let's throw this in here and see what happens. So it's pretty interesting. So even when Einstein had mathematically proved the existence of atoms, they knew they were real, but they didn't have any mathematical models to prove the existence. He did that just through the fact that they move. We know atoms exist now. We can split them, hydrogen atom, woo, hydrogen bomb. We know that they exist. And we can play around with different particles. We have the Hadron Collider now. And with that, and we still use those equations to determine the shapes of nanoparticles. I cannot tell you how many times I swore at the DLS machine, because I always got a noise peak at 1,000 meters, which is about the size of a cell, when I was working in nanoparticle research. And so we use dynamic light scattering, the way that particles reflect light back and how they move in a solution, to determine the size of them. So math has always found a way to lead us in the right direction of that we could see that light was bending around an eclipse based on gravity. It's freaking amazing. So yeah, if you don't like math, that's okay. But you can at least appreciate the fact that theoretical physicists can sit there and come up with these beautiful equations to explain the interactions between different things and how it fits within the observable world, and predict how it would be in something on the quantum level. And quantum level is pretty spooky. But that's going to be the future, man. Quantum computing. Can't wait. See, I love how XKCD put it. Math is just physics understrained by precepts of reality. Yes, but math can also lead us in the direction of where we need to go in order to prove the things work and exist. That's the thing that's cool about math. So yes, if you have questions or anything like that, you can always leave them in the comments. You can send me direct messages on Twitter. You can use the hashtag HeyScientistMel, and I can go and answer your questions there. I do the best that I can. And if I don't know the answer, but I have somebody on hand that can answer it for you, I'll tag them in a tweet and say, hey, can you help out my friend here? You have that knowledge on hand. You would be able to get it a lot easier than I can, which makes being a science communicator super awesome, to be able to network with different people who have lots of different skill sets, to be able to say, hey, I got you. So do check that out. So we're about to wrap up here. I guess we can talk a little bit before we wrap up. We can talk a little bit about what's to come up on the shows. Sunday, guys, Sunday, we have a new episode of Oral Audacity coming out. Doc was indisposed last Sunday, but this Sunday we're coming back. We are going to talk about cold readers, those individuals who pretend to talk to your dead family members. And we have wonderful examples of how they have gone completely wrong, and how they act out in video when they're wrong, which is a lot of fun, because when they get called out for being wrong, they double down. They absolutely double down. No, you're wrong. You're wrong. These dead people are telling me things. So we'll have Omni Eris from PvP. That's a show that Doc is on Saturday evenings. He's on that channel, and they talk about all kinds of stuff. And it's a completely different show from our Oral Audacity, but it's still kind of fun nonetheless. So check that out. So he will be on this Sunday. The following Sunday, on September 8th, Oral Audacity, we will have Jeff Holiday to talk about anti-vaxxers. And that's particularly close to Doc's heart, because Doc has worked in vaccine technology. And so we're going to kind of tackle anti-vaxxers on that. So Jeff will join us. That's at 3 p.m. Central on Sundays, Oral Audacity. And then the following Sunday, We have Dr. Stephen Hobbs, who is, he focuses a lot on animal vertebrates and that sort of thing. We'll talk about cryptozoology. So Doc is all about the Loch Ness. He's like, I got that. So he's excited. So the next 3 Sundays are going to be a lot of coolness going on with that. Yes, I do have a shop, scientistmel.com/shop. I have somebody, Godless Journey on Twitter, is currently going through and reorganizing my site for me. So I'm pretty excited about that. You can check out my shop. You can find t-shirts associated with the show. We have mugs, Cam Girl for Science. We have bags, mugs, t-shirts, all kinds of stuff. I have a section called Blocked By, where all of the proceeds, we take poor behavior on the internet, poor behavior that people exhibit on the internet, we turn it into t-shirts and mugs and donate all the money to charity. Organizations include the World Wildlife Foundation, the American Anxiety and Depression Association. We also have the Trevor Project, Planned Parenthood, all kinds of different good organizations that we donate the proceeds to. So, you know, you can help us out by doing that. If you like what I do have chats on Sunday mornings at 10 a.m. just for my patrons. So, and those pledges start at just $1 a month. Patreon.com/ScientistMel. And we'll talk about all the different ways that you can find me. All right, Peter says, I only have one question. How can I stop my brain from spinning? Stop drinking so much, Peter. Stop drinking. I know you're probably not doing that, but I'm just saying you can do that. Let's see. Nether says, apply equal and opposite counterforce and make the world spin on the same vector and speed. Oh my goodness. All right. String theory. Bull, do you have anything to add before we wrap up here?
No, I'm good.
Nothing to add. All right. So what did we talk about today on string theory? These are the questions we've kind of answered. We've talked about what is it? What is the evidence? There really isn't any. But, you know, mathematical models do lead to all kinds of directions of where we need to go in order to find what we've got to zero in on and make instrumentation for. What are the issues? We've talked about that. Huge amount